I will present this this recent work with Jean Dolbeaults, David Gontier, and Fabio Pizzichillo, which has a lot of names in it, Keller-Lieb-Thirring and Dirac. So I will go by small steps to introduce all of the ingredients, and then at the end I will. I think that the slides are slightly technical, but I will try not to be too technical in everything that I explained. So I will start very slowly, and then at the end maybe skip a few of the more technical things. So maybe to have the very, very basic idea, where are we working with? If you've ever taken a physics course on quantum mechanics, one of the motivations that is typically given is that, okay, if you would have this planetary model where an electron orbits an atomic nucleus, then this would emit radiation, and so the electron would fall into the nucleus. And this is not what we observe. Atoms are stable, and then this quantum mechanics describes this, because if we take, I'll take a little bit, take our lines. In quantum mechanics, we the energy of the electron is given by a Schrödinger operator, so minus Laplacian, divided by twice the rest mass of the electron. This is the kinetic energy. And then the potential, which we think about in this context as something attractive, attractive potential. So if we want to describe atoms or molecules, this is the setting, that the potential, okay, the way it's written here, it's a positive function, and it goes to 0 at infinity. So minus the potential, we have a potential well that confines, since we subtract it, this is the graph of V. So minus V is the other way around. This is a well, and this will confine the electrons, or a certain number of electrons. So you say, yes, because, okay, since this kinetic energy will become very large if the electron is very localized, we have Heisenberg's in uncertainty relation, and that's what avoids that this electron falls onto the nucleus. And as a proof of that, you solve the hydrogen the hydrogen atom, and there you can solve everything explicitly, and you can show that this lowest eigenvalue of this Hamiltonian, that's what's written here, lambda 0 of V, is what's called the ground state energy, or the lowest eigenvalue of this kind of Hamiltonian. You can show that it is finite if V is 1 over x, 1 over modulus of x. Then you have exactly the hydrogen atom, and you can show that this is finite, and then physics moves on to the next. And actually in the 60s, 70s, I think that in mathematical physics, all the tools were available to start investigating this a bit more rigorously, because, okay, the hydrogen atom is one of the only potentials where we can solve it exactly, where we can find the infimum of this spectrum, or this lowest eigenvalue of the Schrödinger operator. So what kind of conditions should I impose on this V, on this potential, such that this lambda, this infimum is actually finite? And I think that was realized by Keller in the one-dimensional case, and was then extended by Lieb and Thirring, was that if you have a V in a certain Lebesgue space, so if you take V, think about V as being non-negative. So if we take V to the power P and integrate it over the whole space in typically dimension 3, but you can also think about dimension 1 and 2. If this is finite, then we can actually have a bound for lambda 0 of V. Why is that? Well, the first thing is that this lowest eigenvalue, you can, it has a variational characterization. This is called the Rayleigh quotient. So lambda 0 of V is for many reasonable V's, the infimum over all, phi in the right space of this expectation value of the Schrödinger operator. And you have to restrict to phi normalized in L2. So this is a variational characterization for the lowest eigenvalue. And then you can ask, okay, if we have a potential with a fixed LP norm, alpha here, what is the lowest ground state energy that we can achieve if we have only alpha of if we have only an alpha of LP norm available? And to do these things, you can actually you can actually have an easy sequence of inequalities if you use as an ingredient the Gallardo-Nirenberg-Sobolev inequality. So if you can start from either end, but if you assume that you know this Gallardo-Nirenberg-Sobolev inequality, I will write it down in a moment, then you can easily bound from below this kind of quantity. So I will show that on this slide. We have the second term, a v, which is actually the integral of v times modulus of phi squared. So we say that v times modulus of phi squared is smaller than or equal to v to the power p 1 over p, and then phi to the power 2 times the dual exponent p prime 1 over p prime. And once you have this, you're okay. So this, on the other hand, the first term, the kinetic term, you can rewrite it as modulus of phi squared, gradient of phi squared over 2m. And then you can use, if p prime is in the right range of values, you can use a Gallardo-Nirenberg-Sobolev inequality. So an interpolation inequality of the form to some power alpha modulus of phi squared. Alpha is already on the slide. Theta to the power 1 minus theta. This controls times some constant an LQ norm squared for the right value of theta depending on Q. So this is the Gallardo-Nirenberg-Sobolev inequality. So if you have this guy here, this one, if you're normalized in LP, is equal to 2. So then you can find that this norm will control this LQ norm to a power bigger than 1. And here, to a bigger power than the one you have here. So then you have a function that will have a minimum, and you can say that you can have a lower bound that scales in this way. You will find out the LP norm to some complicated power. You can see here that this makes sense if p is sufficiently larger than d, strictly larger than d over 2. Otherwise, it explodes. And you can find out some constant which is related to the sharp constant in this Gallardo-Nirenberg-Sobolev inequality. So Gallardo-Nirenberg-Sobolev inequality plus a Hölder inequality gives this kind of inequality. I've been kind of skipping all the detailed steps where you figure out exactly what's the constant and so on. But I hope that you can figure out, if you sit down and take half an hour, you will find what's this constant and how it's related to this other one. So that's the first step. That's how it works. If you have a Schrödinger operator, as soon as you know that your potential is in a certain LP space, you can control the ground state energy by the LP norm of the potential. And then you can ask, is it possible to obtain equality in this inequality? And then you have to, we have two ingredients, so we should have equality in both. So the phi will be the optimizer for this Gallardo-Nirenberg-Sobolev inequality. And moreover, here to have to obtain equality in this Hölder inequality, you need that V is proportional to some correct power in terms of P of modulus of phi. So you find exactly that the potential will be some power of modulus of phi, and phi will be the minimizer of this Gallardo-Nirenberg-Sobolev inequality. Another way to say the same thing is to say that phi is actually the solution, because phi will satisfy minus Laplace on phi minus v times phi equals this number, some constant lambda 0 of v times phi. And now I'm telling you that v is modulus of phi to some power. So actually, if I substitute here modulus of phi to some power q, which you can also figure out with a little bit of patience, then you see that phi is actually also a solution to the nonlinear Schrödinger equation. So we have this beautiful connection between three things: the Gallardo-Nirenberg-Sobolev inequality that's here, the idea of it's a bit related actually for Lieb and Thirring. This was the motivation, the stability of matter. That's to say, in general, what can we say is if we take m nuclei and n electrons, is the lowest energy bounded from below by some constant times n plus m? Or can I get lower and lower and lower by adding and adding and adding more and more electrons and nuclei? Because that would be bad news. We would not be here. But luckily, stability of matter holds. So this kind of ideas of minimizing eigenvalues, and the idea of studying nonlinear Schrödinger equation. So this is a time-independent nonlinear Schrödinger equation. And if you take this solution depending on space and multiply it by e to the I times this eigenvalue times t, then you have a solution which is called a solitary wave solution to this kind of nonlinear Schrödinger equation. So these are the three key ideas. And for Schrödinger, so Lieb and Thirring's paper was in 76. So everything is very well understood. Okay, are there any questions so far? So I can't look at anything except the window that I'm sharing. So I'm sorry for that. But if you have any questions, please just interrupt me.
Oh, nothing so far. Yeah.
Okay, thank you. Okay, then the other part of the long title was the Dirac operator. So again, we go back in time to
sorry, Hanne, I think I forgot. Yeah, so what assumptions do you have on B for?
Actually, yes, I've been extremely sloppy because I wrote here a sum or a difference of two unbounded operators. So I've not said anything about on which domain I'm considering it. Luckily, once you know that this quadratic form is bounded from below, and that's what this inequality gives you. So once you know the Gallardo-Nirenberg-Sobolev inequality, basically, then you can take what's called the Friedrichs extension. So you know that there's a unique self-adjoint extension of this operator with domain included in the form domain. So once you know that you have a Friedrichs extension, okay, we know that for all v in LP, this form is semi-bounded from below. And then, okay, phi in H1 and v in LP. And then, so then you have the operator, and this infimum will be the lowest eigenvalue, and so on. So one of the things we got accustomed to with Schrödinger operators is that you don't have to worry too much about the domain, as long as you assume v in LP with p larger than d over 2.
Okay.
Okay. So this does not include the Coulomb potential, but because of the slow tail, because yeah, it's a power, so it's not in any LP space. But okay, you can, instead of bounding the lowest eigenvalue of the whole Coulomb potential, I have a very hard time making straight lines in this setup. I will try to do a little bit better. So, okay. The Coulomb potential would be something like this, which is, of course, not in any of the LPs, but we can write it as a sum of a piece that's in LP, like this one. Something that is like Coulomb here, and then it's equal to 0. And a piece that is bounded. So the piece that is bounded is not going to bother you too much, not for the domain, and not for making the infimum minus infinity. And then this piece will be in LP spaces. You have still a lot of space here to choose. Maybe also something to mention a little bit more about these names is that in general, a Lieb-Thirring inequality is something way more powerful than what we are considering here. It's an inequality that's not bounding only the lowest eigenvalue, but a sum of all the negative eigenvalues to the right power by an LP norm of the potential. So this is a lot more powerful. And then if you say Keller-Lieb-Thirring inequality, you refer to something that's only bounding the lowest eigenvalue. Okay?
Yeah, thank you.
Okay, thank you. Okay, so now back again to the beginning of quantum mechanics, because there was another issue, not only the electrons falling into the nucleus, but there was the issue of being compatible with special relativity. And that's not the case for the Schrödinger equation. The Schrödinger equation is compatible with Galilean invariance, which we know is not is a good approximation as long as everything moves at low velocities, but it's not the end of the story. So Dirac looked for a way to replace Schrödinger's equation or Schrödinger operators by different kinds of operators that would combine a bit the best of both worlds, that they would have the same dispersion relation as the Klein-Gordon equation. So the relation between energy and momentum would be something like energy squared equals m squared plus wave number squared. So here there are no h bar equals c. H bar already in the Schrödinger equation, I didn't write it. I keep the mass because it's relevant to make the connection with between Dirac and Schrödinger. So he wanted this kind of relation to hold. So this is okay, if you want to put c, this is c to the 4, and so if k equals 0, this is e equal mc c squared, right? This is like the most famous physics equation probably, or one of them. But actually, if you have momentum, then you have to sum the momentum as well. And what do you get? So, okay, but Dirac wanted this dispersion relation, but he wanted it also to be first order. And then he was led to this kind of expression. So a sum of first order derivatives in all the directions. So J is X, Y, Z, or 1, 2, 3, the partial derivatives in all the directions. And M is a mass term with some coefficients such that, okay, if you replace this derivative by the kth component of the wave vector, then and then you square it, then you should have this. Okay, if you square this expression, you will have this the square of a sum. So you will have the squares of each term. You will have, but then you will have cross terms. And all these cross terms have to cancel if you want to get to this nice relation. So in order to do that, it's not possible if these coefficients are just numbers, because they would have to anti-commute. They cannot anti-commute if they're numbers, but you can introduce matrices such that this relation holds. So you introduce a new number n that depends on the dimension. And n is the number of components of each wave function, which then you start to call a spinor, because it's not a complex number, just one complex number, but it's a vector of n, capital N complex numbers. And then you can act on it with this operator. So maybe just for definiteness, if you have just one dimension or two, then you can take n equal to 2. And then you can take as the alpha matrices, you can take the Pauli matrices. No, sorry, it's just in one dimension. If you have 3 dimensions, you take n equal to 4. And then you have the Dirac matrices that Dirac introduced. But actually, you can take many choices of matrices. And the important thing is that the anti-commutator, so alpha j times alpha k plus alpha k times alpha j, is proportional to 0 if j and k are different. And if j is equal to k, it's equal to the identity matrix. The anti-commutator of all the alpha matrices with the beta matrix is also 0, and the beta matrix squared is equal to 1, or to the identity. So then this is an operator, and the proposal of Dirac was, okay, instead of taking minus Laplacian divided by 2m, we take this guy. Why would this be a good idea? Well, if you have this relation, so E will be the square root of m squared plus k squared. And then if you think that k squared is very small, then this is just m plus, and then you Taylor expand. So you will have the square root of 1 plus k squared over m squared. And if you Taylor expand this square root, you get exactly m, which is a constant term in the energy, plus k squared over 2m. So this is the kinetic term from Schrödinger, and at least formally, you can obtain it from Dirac if you Taylor expand for small values of k, so slowly varying things, slowly moving things. Okay, this is something we can all do, but we made a big error in solving this equation by postulating this, because actually there are 2 branches of solutions, plus and minus. And so the big inconvenience of the Dirac equation is that if you just take this operator, which is the one we would like to use to replace the Dirac operator, if we take just its spectrum It's absolutely continuous, just as the spectrum of the free Schrödinger equation, but it are the solutions of these equations for all possible values of k. So it's the whole line from m to plus infinity, and the whole line from minus infinity to minus m. This is a spectrum of dm. So a ground state, here the energy already, if we have only the Dirac operator, can go to minus infinity. And this led to, Dirac proposed an interpretation because electrons are fermions, and we imagine that all these negative energy states are occupied by fictitious fermions. This is the idea of the Dirac sea. So this is occupied. And then an actual electron would have to float on top of the sea, so to go to the positive, or at least above this infinite reservoir of negative energy fermions. This was really revolutionary because it led to he also predicted that then one of these virtual fermions could become real, and there would be like a hole in the sea of fermions, which would correspond to an anti-electron, or what is called positron, which was observed later and led to a Nobel Prize for Dirac and so on. So this whole Dirac equation also led to that saying then that's actually we should abandon this simple quantum mechanics and start studying quantum field theory, or second quantization, where particle numbers are also variable because you can create a pair of a particle and a hole and so on. So this is one of the reasons I think that for which just this operator by itself has not been studied as much as Schrödinger operators, because once you start touching Dirac, you almost immediately start touching second quantization, and you move on to quantum field theory. But recently this has changed a little bit, and I think one of the big things that motivated this was the discovery of graphene, because in graphene you find the same expression to effectively describe low energy electronic excitations. Effectively, that means that actually there's not an infinite reservoir of negative energy states. It's just finite. But if you zoom in close to this, close to the low energies, then you're well described by a Dirac operator. If you have pure graphene, it's a massless Dirac operator, but still, there is interest in studying this Dirac operator just as a single particle operator. Okay, so, what have we said? We have a complicated, we have a first order differential expression that acts on functions from Rd to Cn, which we decided to call spinors because everyone does so. And if we have just this expression, then the spectrum is the half line from minus infinity to minus m and from m to plus infinity. Still, if we add a potential, what we expect is that eigenvalues will appear, I don't see my cursor, in this, what's called the gap, the hole in the spectrum around between minus m and m. And so we can still ask, okay, if this potential is an LP and it has a small LP norm, is it true that these eigenvalues will be maybe close to m, or how can we bound the distance from this eigenvalue to m by the LP norm of the potential? So that's the question we decided to study, and that's what the title is about. So I spent like half of the talk explaining the title, and now I'll give some results. So on this slide is the same, just to check, this is everything I've already said. We want to ask this question, okay, there are many challenges. The first thing that I've already explained is that the Dirac operator is not positive semi-definite. So many of the tools that we have for Schrödinger are not available. It's not scale invariant, which is a challenge and an advantage. For the Schrödinger case, we could have a very nice bound by a power of the potential. We cannot expect this to happen for Dirac because it's not scale invariant. You cannot scale out the LP norm. But so because it's not positive semi-definite, I already sketched this idea of Friedrich's extension and so on. One of the first challenges is to define or find a self-adjoint extension of this sum of two unbounded operator, and then how to define a ground state, because we cannot say that it's an infimum of anything, because the of the expectation value, because we know beforehand that this will be minus infinity. And so actually, when we started, we say, okay, this is we were very ambitious. There are lots of problems, and then we started realizing that some of them had been already solved. How to define a self-adjoint extension? There are several possibilities, and actually, the oldest one is a very general framework for perturbation theory, where you define a perturbation of an operator by defining a perturbation of the resolvent of the operator. And that's something that's has been used a lot for Schrödinger, but you can also use it for Dirac. It is not using a positive definiteness of the Laplacian in any sense. So this works nicely. There are other ways to define self-adjoint extensions for Dirac operators, because there is actually a variational characterization for the eigenvalues due to these authors. And actually, you can use this variational characterization to define an operator in a very analogous way to the Schrödinger case, but it's a lot more involved. You have to be very careful about spaces. And then for the eigenvalue, so these are the results about defining operators. And about maybe ways to capture their eigenvalues. Specifically, for a way to capture the eigenvalue, estimate the eigenvalues, there are many results on Dirac-Coulomb operators, also very precise results on the domain. So Dirac-Coulomb is just Dirac minus Coulomb potential, so something that's singular as 1 over modulus of x in dimension 3. And it's very tricky. And there are also results on bounds for eigenvalues, but not optimizing in the potential. It's more like bounding the eigenvalue by using a kind of Birman-Schwinger principle. So the things that we will use, so I will say first how we can overcome these two major challenges, not positive semi-definite, and how to find the self-adjoint extension and how to define a ground state, how we overcome them. And that's by introducing a Birman-Schwinger operator. If you have a potential which is just scalar valued and non-negative valued in LP, you can define this operator. So you have square root of V, the resolvent of the free Dirac operator at the value lambda, and the square root of V. And the important thing of this is, okay, V is small if X becomes large, because it's in LP. Small is to take very heuristically. And this one over this is small if the kinetic energy is large. So you have the product of something that's like confining in V and something that's confining in Fourier space. And so you can hope that this is a compact operator. And this happens if P is sufficiently large, larger than or equal to D, and strictly larger than 1. This operator is compact, and moreover, if we move this parameter lambda, okay, this parameter lambda is allowed to be any complex number away from the spectrum of the free Dirac operator. So if you move it very far away from the spectrum of the free Dirac operator, this resolvent goes to 0. And so, for instance, if you move it on the imaginary axis out to plus or minus infinity, the operator norm of this operator goes to 0. And this is what allows you to define a resolvent, to put ourselves in Cato's setting, as the free resolvent plus something that involves this Birman-Schwinger operator, and it will actually be a compact operator. So the theorem of Cato then says that this sum of unbounded operators has a self-adjoint extension such that its resolvent has this expression. So the first thing is that you can check if everything are just matrices, there are no unbounded operators involved. This is actually the resolvent of dm minus v. But if not, if you don't know if that dm minus v is a self-adjoint operator and so on, you can get a self-adjoint extension, single out one of possible self-adjoint extensions even, by defining first its resolvent. Moreover, when is this resolvent going to be singular? It's going to be singular when this expression here blows up, and that's when 1 will be in the spectrum of this Birman-Schwinger operator. So I will skip what's exactly, because once you have this expression, you can do you can say, okay, this is very implicit, we want to be a little bit more explicit, and that's something you can do, but I will not do it. But the important point is that the Birman-Schwinger principle holds for this self-adjoint extension. That means that Z is an eigenvalue of dm minus v. And now if I write this, I mean the self-adjoint extension defined by using this expression here. If and only if 1 is an eigenvalue of the Birman-Schwinger operator with parameter z. Z is the one that I will maybe square root of v r0 of z square root of v. And I think I've never said what is r sub 0, but r sub 0 is the free resolvent. So r sub 0 of z the free Dirac operator minus z inverse. Okay, that's a whole lot, but it means that we can define a self-adjoint operator, and we have a way to avoid to go into the very fine details, as long as we have a v in LP with p larger than or equal to d, to the dimension. Then we can find a self-adjoint extension of this sum of two unbounded operators easily. And also we can capture the eigenvalues of this unbounded operator by studying the eigenvalues of this family of compact operators. So here we have operators that are maybe complicated to study, but z is just the eigenvalue. And here we have operators that are very nice to study, but z is included in the definition of the operator in a nonlinear and maybe stranger way. Okay, this is the Birman-Schwinger principle. That's also an important tool in at least one of the possibilities to prove this Lieb-Thirring inequalities that bound sums of eigenvalues also rely on this Birman-Schwinger principle. So I call this step 0 because now we have an operator, so I can state theorem. First, what is the eigenvalue that we are going to study? We are going to study this operator dm minus v. We are going to take the smallest point in a spectrum that's strictly above minus m, because we had essential spectrum here and here, and then eigenvalues here. So we take the smallest of these eigenvalues for some given potential. And then the capital lambda d, that depends on two numbers, alpha and p, is the smallest possible eigenvalues for all potentials with given LP norm alpha. Okay. I can define these things. Maybe this lambda d of v is equal to minus m. That's possible. And maybe this, by definition, it's above minus m. So maybe this is always equal to minus m or something like that. When we started working on this, we really had no idea what we were going to find. Is it possible that for all LP norms, the lowest eigenvalue, for all small LP norms, this lowest eigenvalue should stay close to m, or not? Can I cook up some strange potential that makes it very low? But actually, things work as good as we could hope them to work, because we didn't even expect them to work. So a first result is about this lambda d that depends on two numbers, but p, we fix p. P is the exponent of the Lebesgue norm. And then we can look at alpha. So alpha is, by definition, non-negative. If v is equal to 0, its LP norm equal to 0, then this number equals m. And actually, the statement is that it's a continuous and strictly decreasing function. So I put alpha here. M here minus m here. If alpha is equal to 0, I'm here. And then I go in a continuous way, strictly decreasing way, until at some point I hit the value minus m. And this some point, I call it alpha c of p. Okay, so if I fix some LP norm between 0 and alpha c of p, I can say that this lowest eigenvalue is going to be bounded from below by this number capital lambda d of alpha and p. Okay, so this is this function, and what we know is that it is nice and it behaves as you would expect, that in the sense that it starts at 0, it's continuously decreasing, and at some point the lowest eigenvalue can cross the entire gap and disappear into the negative essential spectrum. So we don't claim to say anything about LP norms bigger than this one, because then this number here would be capturing actually like something like the second eigenvalue or something like that. And then it becomes very difficult to hope for any clean statement. Okay, so this is the first part. And then the second part is that there exists a potential V such that this value, this capital lambda d, is actually an eigenvalue. And the associated spinor solves an equation. So psi is the eigenfunction and V is the potential. The potential is proportional to a power of the modulus of psi. Now psi has n components. So the modulus of psi is really the Euclidean, the sum of the first component modulus squared plus the second component modulus squared and so on. But still V is a power of this quantity. And the nonlinear equation is very analogous to the nonlinear Schrödinger equation. And also, to be consistent, the LP norm of the potential should be equal to alpha. So that's this equation. So in particular, we show that there exists a solution to this equation. And finally, as in the Schrödinger case, but quite surprisingly, since we don't have any scale invariance and so on, there is an explicit solution. It's quite a lot harder, uglier to read and harder to write down than the Schrödinger case, but it's there, so you can plot it. So I will skip all the steps of the proof, maybe just point out that the whole proof is really very strongly relying on this Birman-Schwinger ID. And this allows to rephrase it in a very beautiful way. Maybe just to take home something about the Birman-Schwinger operator. This is just a plot of, for some given potential, of the eigenvalues of the Birman-Schwinger operator as a function of z or lambda, as lambda moves from minus m to m. Here m is equal to 1, but that's not important. And you see that there are positive eigenvalues that become bigger and bigger because the resolvent will blow up. So this is a spectrum of kV of lambda, these blue and red lines. And here on this axis we have lambda. And at each time they cross m, they cross 1, sorry. Here we have eigenvalues. These are the eigenvalues of the Dirac operator minus this potential. Okay. So this is the Birman-Schwinger principle, and this is what in the end allows us to study the whole problem. So we have exact solutions in one dimension. We plotted them here. They're in two plots because there's no nice monotonicity with P. So it's very hard to tell apart the curves. Close to here, they should behave like the Schrödinger analog, so like powers, but then they start to do different things. And so in one dimension, since the solution is explicit, we can show that it's the upper component, the V is even, and there's a unique solution because you have an ODE that has only one solution that decays at infinity and so on. But this leads to many open questions, and I think the most I don't know, one of the very tempting ones to try to answer is if in general in higher dimensions this optimal potential is still radial. Even if we would a priori restrict to radial functions, we can decompose in angular momentum, but we cannot a priori say that the lowest eigenvalue will be the one with lowest angular momentum. And one of the other questions we are thinking about right now is, for now we had written this, and actually here understood there is the identity matrix in Cn. You subtract like a scalar. You can of course replace this by other matrices. One is beta, the matrix that goes with the mass, and this is formally everything works the same, and the nonlinear equation you find is more interesting, I think, than the nonlinear equation that we find here. So that's also one of the things to study. And just to illustrate why I find this question like challenging, but it should be true, is that David realized some numerical simulations. So you start from a random potential, and then you find the eigenfunction corresponding to the ground state, and you take the right power of this eigenfunction to the right power as a new potential. And you iterate this 0, 2, 4 times, and it becomes very, very much a radial function. But this is, of course, not a proof of anything. So I think I've been talking a lot, so I'll stop here. Thank you very much. And please, if you have any questions, just go ahead.
Thank you, Hanne. So is there anyone in the audience who has some questions for Hanne? I have a few questions, but I'm just waiting for someone else to.
Okay.
Maybe Frank was too timid to ask question in English. Maybe he can, if he,
Yes,
if he
you
wants.
can.
I have the question. Can this Lebesgue-Thirring inequality for the Dirac operator be used for some stability of matter for some system of n particles?
Well, this was one of the open questions that I could have asked to the added to the list. For now, what we are bounding is the lowest eigenvalue. And I'm not completely sure what is the full status of stability of matter when you use relativistic. It's a good question. Yes. So okay, this is a very basic kind of stability of matter, in the sense that, okay, as long as your LP norm of the potential is not too big, then the eigenvalues stay close to m. So you're not radically different from the Schrödinger case. But towards the many body, with Dirac is very, very hard, and I'm not sure what's the state of the art there. So I don't know.
Okay.
Are there any more questions? So I think I have some, but they are also like from an outside point of view, like from someone who doesn't know much about this operator. So maybe I will ask the one which I mean, so what you were trying to explain to us some after the Schrödinger part, the genesis of this Dirac operator, and I still didn't understand why we need to look at this, and what is the extra information you might obtain which you don't see in the Schrödinger.
Well, the idea is that there are different operators, and they're both so what you know, or what physics tells us, is that the Schrödinger operator is not a good description of the kinetic energy when k becomes close to the velocity of light. Basically, that's the point. So you replace it by this Dirac operator, and then your kinetic energy does not longer grow like k squared, but for a large k, but more like k. So this is a weaker. This kinetic term is weaker in many senses. So you would like to know, okay, if we replace it by this weaker kind of kinetic energy, can we still does this still have enough strength to avoid that the electron falls into the nucleus? And actually, for instance, for Coulomb potential, so if we take dm, so this is not either my specialty, but there has been a lot of effort to study this in 3 dimensions. And it's actually the electron does fall into the nucleus if Z is too large. And too large is something I will probably completely mess up, but it's something like 200 or something. So as we are observing heavier and heavier, so for Schrödinger, this is bounded from below for any value of Z and so on, and you can scale out the value of Z, and there's no problem at all. But for Dirac, it's not possible to define a distinguished self-adjoint extension. So to make sense of this operator in a canonical way, if Z is too large. So you see that there are these relativistic effects come into play and may be important in some contexts or not. So I think it's important to have rigorous information for when are they important and when can we safely use a Schrödinger operator instead. Is that a bit an answer to your question?
Yeah, I think so. And I would like maybe a good starting point to understand something about the Dirac operator. If you can maybe send.
Yeah, there's the book of Thaler. It's the book. It's a physics book, but I think it's a good starting point because you find all the expressions. You find all, and I mean, it's a physics book. But it's not really. Let's say it's a mathematical physics book. It's called Thaler, and it's called the Dirac operator or the Dirac equation. I think the Dirac operator.
Okay, thank you. And another thing which I didn't really understand, when during at what point during this talk you departed from the linear, meaning I saw in the beginning linear Schrödinger operator. I didn't see when we switch to nonlinear, and also I don't understand why this Dirac thing here becomes nonlinear.
It's just okay. So you have this kind of inequality, and then you ask the question about optimality. Is there a phi and a v such that this infimum is attained? And since I said that this was a consequence of two inequalities, this Gallardo-Nirenberg-Sobolev one and this Hölder one, you need to have equality in both to have this. And the easiest one is if you want to have equality in Hölder. Okay, if you want to have equality in Cauchy-Schwarz, they have to be proportional, and here it's Hölder, so you have to take into account the values of p, but v has to be proportional to a power of modulus of phi to have equality here.
Yeah,
and that's
so this
what
is
makes you replace the v that would come here.
That's the basis for your algorithm. Is that the basis for your algorithm? Like,
yes. So okay, the algorithm is really a tool to get heuristic IDs. We have no proof that this is converging or in any sense. But the basis ID is that, like, to take as a next if it gets stuck in some point, if it converges to something, this something will at least be a solution to the nonlinear equation. We are not sure that it's optimal, but
and in what sense you want it to be optimal? That is not clear, because here you may have many solutions for this, meaning v and phi. I mean, so
you have yes. So in higher dimension, this equation has many solutions.
Yeah.
And you guess that one of them, but with different values here. And you guess, you expect. This happens for Schrödinger as well. Actually, I'm writing with Schrödinger. Okay, so this equation has many solutions, and you expect that there is one where phi does not change sign, and this number is the smallest possible. And that's like the ground state of this nonlinear Schrödinger equation as well. And for Dirac as well, we expect that there is one where the components of psi are oscillating as few times as possible. And that this will be the solution, and that this will have the smallest number over here, so the smallest eigenvalue.
Yeah, and is this solved? I mean, so the questions you asked at the end are related to the Schrödinger or the Dirac with the optimal potential.
So for Schrödinger, you can find out that you can use, for instance, you can use rearrangements to show here that the optimal potential is radial, or you can look at, you know that, oh, okay, you can use rearrangements to show that the solution here is radial, and then the solution. But as well from here, you can use it, and this is something that we can't do for Dirac, or we don't know how to do for Dirac.
Oh yeah. Yeah, meaning, and so in the case of Schrödinger, is it like the Hardy potential inequality or
no, not really, because Hardy would be with 1 over modulus of x squared. And that's not in any LP space. So here really the solutions are the optimizers for this Gallardo-Niedermeyer-Sobolev that are not explicit, but they exist and they are nice and exponentially decreasing and unique up to the symmetries of the problem and so on.
Okay. Yeah, I think it's more or less I have like questions. Yeah, but it was certainly very interesting, and it made me think about some other things also. Like, I mean, I saw some papers some time back about when I was looking at some Hardy type inequalities, like some works by optimal Hardy potential or whatever by Pinchover and group of people in Israel. And so I don't know if you may find some inspiration maybe in
Yes,
there.
maybe.
Yeah. I mean, here, for example, do you have for the and so the Dirichlet thing here, I mean the Dirac, forgive me, um, um, you were looking at like the minimization or ground state with some at certain levels of energies, the alpha, I think it's like you fix and then so I didn't see the non-homogeneity of the operator. I mean, it's because this operator is non-homogeneous, you have to do.
No, it's because you have this M. You have a master, and so you cannot scale. In the Schrödinger case, you can if you divide the potential by some number to make it LP norm equal to 1, then you can rescale the lengths such that you get out just a factor. But this is something that you cannot do for Dirac.
Yeah.
If you have this.
Yeah, that's probably not a big issue. And so if you have like results on like is there like some maximum principles for these kind of operators? You know, if
No, yes, there is what's called a min-max principle, because okay, if you would want to capture like the second eigenvalue instead of a minimum, you would have a min-max, but over eigenspaces of you would have a minimum over spaces of dimension 2 of the maximum of the Rayleigh quotient. But then here you have infinitely many energies below. So then you have a minimum over subspaces and a maximum over a complementary. And if the operator is nice, the potential is nice, it's easy to write down, and there are many results that rely, especially by Levin, Esteban, Los, that rely on this technique, and so this is also the technique we try to use in the first place for this problem, and we were quite surprised that actually like the old way maybe of using the Birman-Schwinger operator make this problem a lot more tractable.
Yeah. 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 Thank you. It was exciting for me here.
Thank
Yes.
you. Thank you for the
Yeah.
invitation, and I hope the next time I will be in Concepcion.
Yeah. And maybe uh, about this thing, the jornada, and I
Mhm.
mean, if not in,
I have already sent an email to her.
yeah,
Ah,
if
okay.
uh, uh, maybe it's if you can't like organize a session, maybe it's
It's a bit.
even
Yes,
no, no,
I'm
it
a bit
would be
afraid.
even better that in some of the national meetings, maybe you offer to give a course on maybe Dirac operators for graduate students. It could be quite like
Yes,
interesting thing to
maybe
know.
I
Yeah,
will have to teach a lot next semester, so I will. I'm a bit
yeah,
afraid
mm,
to take too many things in between.
yeah,
But
yeah,
thank you
yeah,
for the email.
yeah. Okay. Um,
Okay, have a nice day and a good start of the year.
and since we are just among the